Back, we're doing our semester review here, and of course the point we want to remember is that these questions are not going away. We're going to be doing them throughout this entire semester. And again, as you guys enter Calc 2 for many of you next year, 73 is our related rates question that we had worked on most often. We had talked about the radius ratio to the height ratio in a cone. So here we're told that water is leaking out of this cone. So the rate that's given is a change in volume with respect to time. And because water is leaving the cone, we're going to make this negative. But look at the units. If you have trouble recognizing what this is, isn't it clear that it's a change in volume with a respect to a change in time? And what we're asked to find is how fast is the height of the water changing at a specific case. So we need a formula that relates volume to height. And of course, you were even reminded of this formula. I hope it's one that you know. But notice we don't really care about the change in the radius here. So we can simplify this formula. Because of similar triangles, we know that the water is always going to have a radius perpendicular to the height, and that ratio is always going to be 1/4 of the height. So we know the radius at the top of the water is always going to be 1/4 of the height, and that can help us simplify this formula into just one variable. So we'll have 1/16 h squared. So now let's simplify here. We'll have pi over 48 h cubed. And now when we do our differentiation with respect to time, we don't need to use the product rule. So the derivative, the constant stays out of the derivative. We do the power rule on the 3 to get 3h squared. And then every variable, we're differentiating with respect to time. So every variable gets a chain rule. And now our specific case is when the height of the water is 40 feet. So this is our specific case when the height of the water is 40 feet. So when we square it, that will be a 1600. Our dv dt was given. And here I could cancel the 3 with the 48 to make this a little simpler. Pi over 16. And we're looking for the dh dt. So here the 16 can cancel into the 1600, so we can divide both sides by 100 pi. And I think probably we would write this as 1 over 50 pi. Feet per day would be the change in height with respect to time. All right, and then in question 74, we're looking for a linear approximation of the square root of 4.1. So our square root function, we know is concave down, and what we're asked to find here is the square root at 4.1, and of course we don't know that, but we do know the square root of a nearby point. So the idea of linear approximation is that we find the equation of a tangent line, and we put 4.1 into the tangent equation because it will be a very close approximation of the point that we're actually looking for. So our point of tangency is going to be 4, 2, and then we need our derivative to get the slope of that tangent line. The derivative of the square root of x is 1 over 2 square root of x, and we put 4 in. So we'll come up with 1/4. So our tangent line is y minus 2 is equal to 1/4 of x minus 4. And then we're simply going to let x equal 4.1. So again, we're finding this red point in our diagram. So when we put 4.1 in here for x, we'll have a 1/10. 0.1 or 1/10. So change to either both decimals or both fractions. And then if I add the 2 to the other side. So there's our approximation. So the square root of 4.1 is not exactly 2 1/40, but it has to be very close. And question B, you have to explain that you know this is an overestimate. Just refer to my diagram up above. This is an overestimate since y equals the square root of x is concave down. In other words, you can see that the tangent line stays above the square root function. All right, now we want to talk about concavity. Concavity comes from the second derivative, so we have to do a first derivative here first, and the fraction is only there to make our second derivative easier. So double check your power rule. We don't care. The first derivative could tell us about local max and local min, but we don't have to answer that question for this problem. So let's proceed right on here. So we'll have a negative 12x plus 9. And we're not going to call these critical numbers. Critical numbers come from the first derivative, but we are going to find out where the second derivative changes signs. So we do want to factor it, and it factors very simply, x minus 1, x minus 3. And those are both single zeros, so we expect that the second derivative changes sign at both of those. But we want to justify our concavity, so we want to test the intervals. So from negative infinity to positive 1, what do we know about the sign of f double prime? So think about, use your factored form here, think about putting in a number like negative 5 or negative 500, and you can see that both parentheses would be negative. So f double prime is greater than 0. So f is concave up. And then we expect on the next interval that it will change signs since it's a single root. So if we try the number 2, we can see that the first factor changes to positive, but the second factor is still negative. So f is concave down. And then again, on the third interval, of course, both factors will now be positive. So f is concave upward. So you need those interval tests to justify your results. And now we've done all the hard work for question B. It's just what about inflection points? Well, we've got concavity changing twice. So we've already done the work. We've already explained concavity. So we can say f has inflection points at x equals 1 and x equals 3 since concavity changes. If you hadn't already used the term concavity changes in your answer to part B, then you could have said, or since f double prime of x changes sign. Remember, it's not enough for the second derivative to hit 0. The second derivative has to change sign. All right, and then we need to find the values that satisfy the mean value theorem. So remember, the mean value theorem says if a function is differentiable, then at least once the instantaneous rate is equal to the average rate. So is our function differentiable? It's a polynomial function, so we know it's differentiable everywhere. Polynomial function f is differentiable. And it's differentiable from negative infinity to positive infinity if you wish to say even more. We really only care about the interval from 0 to 4. So by the mean value theorem, there is at least one value of c somewhere between 0 and 4. So here we want to switch to the open interval where the instantaneous rate, that's the slope of the tangent line, so that's the derivative, is equal to the average rate, that's the slope of the secant between the endpoints. So this endpoint should be a 4, and the other endpoint at 0. And now you could do both sides at once here. F prime of c, look at the derivative here, just by the power rule, and I'm just using c as my variable. So the derivative, 2c minus 2, should be equal to this slope. F of 4 is 16 minus 8, which is 8. F of 0 is 0. So we want 2c minus 2 to be equal to 2. So 2c is 4 and c is 2. Now, how come we actually had to find the value of c here? We'll read the question. It doesn't say just is there a value of c. Here it actually asks us to find the specific value of c. These problems are posted on our class website, so please print again and rework them on your own until you are completely confident. So each of these problems has to become easy for you.